So, hello to everyone who's watching on YouTube. We'll get started with the session in 5 or 10 minutes. I'm just waiting for a few people to join the session in person. So, yeah, if no one joins the session in person in 5 10 minutes, I'll anyway start the session for the YouTube audience. So, yeah, I'll be starting like something like 10 minutes. Okay. Hello, Manas. So let's wait for like 3, 4 more minutes. So maybe a few others can also join the session. So yeah, I'll just get started in 3, 4 minutes. Okay, so I guess no one else is joining the session, so maybe we can get started. So, hello Manas, just to reintroduce myself to you and the YouTube audience who's watching this. So I'm Lakshay Sagi. I'm the problem solving TA for the NPTEL Games and Information session. And this will be, I believe, our seventh session. And in this session, we'll be discussing problems related to extensive form games. So basically, last time we discussed problems related to like dynamic games, and but we did like in the last week of lectures, they like these games were not exactly quantified. But yeah, this week, like we'll be discussing problems related to extensive form games and their normal forms. And while doing so, I'll be assuming that everyone has gone through the lecture videos, and we'll be focusing more on solving the problems rather than discussing the theory again. But again, like since all of this is a bit theoretical in nature, so the questions will anyways be also a bit theoretical in nature. So there's that. So yeah, and yeah, just so Manas, just to remind you that if you have any point at any point of time you have any doubts or there are any technical issues, feel free to type in chat and inform me so that I can try to rectify it to the best of my capabilities. So maybe I'll just get started. Like I'll just share my screen and we can get started with discussing the questions. Today's problem set will also be more or less theoretical in nature because yeah, last 2, 3 lectures have been more theory based only. So we'll be discussing a bit more theoretical questions rather than actual uh, numerical problems. So there will be a few numerical problems, but yeah, let's just get started. Okay, so I hope my screen is visible. If it is not, like, you can type in chat and inform me. Otherwise, maybe let's get started. So just as a revision of what actually is a normal form game, like s- so just as a revision of what is actually a normal form, what is an extensive form game. So this is just a definition straightforward from the lectures, but I just thought that maybe we should revise this definition because yeah, this is something which is a very standard definition, and yeah, the theory is built around uh, this standard definition of what an extensive form game actually is. So it's important to know the specifics behind it. Although it's not too difficult, but still, yeah, it serves as a good reminder for us. So, so an extensive form game is just a tree with a specific vertex which indicates the starting point of the game. So note that one important point of the extensive form game is that it is a tree. Like, it's not a, and what's a tree? Tree is basically an acyclic graph. So an extensive form game does not have cycles in it. It's an acyclic graph, and a specific vertex indicates the starting point of the, like, there is always a unique vertex, like there's a specific one vertex which indicates the starting point of the game. So there cannot be multiple starting points of the game. And a cost for each player at each leaf node or a terminal node. So for every leaf node, so leaf nodes are usually nodes with a degree 1 in a graph. We know what leaves are in a tree, right? So in a leaf node, the cost for each player, so there is a cost associated for each player at each leaf node. And we can assume that these leaf nodes actually correspond to, like, end of the game. So every leaf node corresponds to one possible outcome of the game. And then a partition of the nodes except the terminal nodes into player sets. So, like, uh, at every node, we'll be calling it belonging to one of the player sets. And, like, what this means is that at every node, one of the players will be taking some action, and the player which takes that action at when we are at that node corresponds to the a player set to which that node belongs. So yes, all of this is just like formalizing the notion of an extensive form game, but it's very easy to see what all of this is. And then there was this discussion around the information sets of a game. So what this means is, so there can be games which have perfect information. In perfect information, like, every player can distinguish what other player has played or what other player has not played. But but in general, there can be imperfect information. What this means is, some player may know what the other player is playing, but the other player may not know what one player is playing. So we'll come to discussion around these questions also, but some examples were discussed in the lectures around this also. So a partition of the player sets into information sets. So every player has a player set, which means the nodes at which that specific player is going to play. Suppose player one has some set of nodes which correspond to the node that which player one has to play something. But now, now this set of player one's nodes will again form a partition of information sets. And what this means is that, uh, like, what intuitively all of these information sets correspond to is that the player one cannot distinguish between two nodes belonging to the same information set. So if two nodes belong to the same information set, then the player one cannot distinguish between these two nodes. So player one really has no way of telling, like, I am at which node of these two nodes. And, like, this you can see encodes, like, information. Like, this means that player one does not have the full information of at which node is exactly the player one present, or something like that. And, like, yeah, same number of branches emanate from the each node in the same information set. This is just for consistency of, like, definition of information sets and everything. Like, if two nodes are in the same information set, then player one cannot distinguish between them. But if they are in the same information set and they have, like, different uh, outgoing degrees, then what this means is player one actually can distinguish between these two nodes because of outgoing degrees. And an additional constraint, which is like which is Usually, in the standard definition of extensive form game, this constraint is usually considered. Like, but it's up to us to like have it as a convention or not, which is this condition of no node is a descendant of another node in the same information set. And this corresponds to the assumption of absent-mindedness. Like this was discussed in the lectures also. So what this means is that in the same information set, no node is a descendant of another node, which actually means that suppose this was true, that a node was a descendant of another node in the same information set. Suppose in player one's like information set partition, there were two nodes belonging to the same information set. Which and they had a ancestor descendant relationship. Now, what this means is, like player one actually cannot distinguish between whether it has played the ancestor or a descendant. So, what this actually means is, player one does not remember even suppose player one plays the ancestor first and then the descendant, then the player one cannot even distinguish between like whether it has even played something or it has not played something. So player one does not even remember whether it has played something or not something. So there's another thing which is like player one does not remember what actually the player played. So one thing is player not remembering what the player actually played. But another thing is player not even remembering whether he has played or not played at all. So that assumption is okay that player one does not remember what exactly he has played. The player one may know that he has played something, but he does not remember what he played. And this is a very valid assumption in real life. Like we don't exactly remember the decisions which we took. But this assumption of absent-mindedness is something which can be considered in case-to-case scenarios, like whether we want to assume this in the game or we don't want to assume. Generally, it's assumed that players are not absent-minded. That if the player has played something, the player may not remember exactly what exactly did the player play, but the player will remember that he indeed played something. So yeah. So I hope this thing is clear. Like if it is not, like you can ask me in chat and I'll try to explain it better. But other than that, I think this is the this is the main thing. This extensive form game definition is the main thing around which this week's lectures revolved. So maybe we can get started then. Uh, so first question is again like just as a warm up is a more theoretical question. Uh, so pick the correct options and the options are so first option says that maybe we can go option by option. So option A. So option A says that a single act game can admit multiple equilibria. So so what are single act games? So I hope Manas you remember from the lectures that single act games are the games where in like any game path every player plays exactly once. So this is what you call a single act game. Like every player is acting only once. And then there was discussion around like single act games admitting multiple equilibria or a single equilibria. Okay, so yeah, in single act games, like a player can play at most once, like not exactly once, but at most once. Yeah. Okay. Like I think it's in single act games, usually it's more of a convention kind of a thing, like whether you want to assume at most once or exactly once, but I think both can be uh mended into each other. It's not much of a difference, but yeah. I think if it was discussed, I don't remember exactly what was discussed in the lecture at most once or exactly once, but yeah, if it was at most once in the lectures, then we'll be assuming that is at most once. But other than that, like let's not get into that the exact definition of single act games. But uh, can a single act game admit multiple equilibria? What do you think, Manas? Yes, so exactly. Yeah. Okay. Yeah. So Yeah, correct, Manas. So a single act game can indeed admit multiple equilibria, and there were some examples indeed discussed in the lectures around these. So there was this whole discussion in the single act game, uh, admitting multiple equilibria around like a single act game can be thought of as like combinations of some dynamic games and some simultaneous games, and then you can actually say that. The equilibrium, the Nash equilibrium of simultaneous game will also correspond to the Nash equilibrium of the whole single act game. So there were discussions like this also. So yeah, actually there can be multiple equilibria. So good job, Manas. So this is correct as discussed in the lecture. So you can draw up an example for the same also. It's not too difficult. And then option B is a single act game can be dynamic. So again, like I just said, like this, what I just like the answer to this also follows from what I had already discussed. So a single act game can be like indeed dynamic, as we said that a single act game can be thought of as a combination of dynamic game as well as a simultaneous game. So yeah, it can be possible that the whole game is just a dynamic game and not a simultaneous. Like I hope like these definitions. So dynamic games are usually games in which players are playing sequentially. So one player kind of uh, knows what the like maybe not know, but they are playing sequentially. Like one player plays first and then the second player plays. So this is a dynamic game and like simultaneous games are where both players are actually playing simultaneously. So yeah, and single act games are can be a combination of dynamic as well as simultaneous games. Yeah, so this option is also actually correct. So this was also discussed in the lectures. And so the C option is in a simultaneous move game, a player can have multiple information sets. So suppose both the players are playing simultaneously. Like so what do you think, Manas? Will this be correct that in a simultaneous move? So what do you think, Manas? In a simultaneous move game, can a player have multiple information sets? Okay, so Manas is writing no in the chat. So yeah, actually that. So good job, Manas. So actually, yes, that. Uh, in a simultaneous game, there won't be multiple information sets. And why is this the case? Uh, uh, this is because what does an information set correspond to? Information set corresponds to the player like not being able to distinguish between two nodes. And now, like actually, in a simultaneous move game, the both all the players are playing simultaneously. Since they are playing simultaneously, then players are actually don't have any information of what has occurred already because the game is not dynamic in nature. So players don't know what actually has happened first or second. So everything happens at the same time, and that's why there will be there cannot be multiple information sets. So as players are playing simultaneously, hence no player has any information about the state of the game. Yeah, basically, like no one knows what the current state of the game is because all of them are playing at the same time. So then option D is in a game with perfect information, each information set is a singleton set. So this was also discussed in the lectures. So what's a game with perfect information? In a game with perfect information, every player knows what has occurred already in the game so far. So yeah, what this means is like every player is actually able to distinguish between every pair of nodes, whether the game is currently at one node or the other node, because everyone has all the information. So yeah, so I think okay, this was incorrect. Like the option C was actually incorrect because players are playing simultaneously, so no player has information about the state of the game, and hence only one information set. Yeah. Okay, sorry for like that. And now the option D was correct. Like in a game with perfect information, each player information set is a singleton set. Like each information set is actually a singleton set. Like yeah, because every information set contains just a single node because player is able to distinguish between every pair of nodes. As a player can distinguish between every pair of nodes in the player set. As in a maybe I should write like this. In a game with perfect information, every player can distinguish between all pair of nodes in the player set. Yeah, something like this. So actually options A, B, and D are correct. Like single act game can have multiple equilibria. Single act game can actually be dynamic in nature because like suppose there are just two players and like both the players are playing once, then player one plays something and then player two plays something. So player two already knows what player one has played and hence the game is somewhat dynamic in nature. And like the C option is incorrect that player can have multiple information sets. So this is incorrect. Player will only have single information set in a simultaneous move game. And in a game with perfect information, each information set is a singleton set. So this is also correct. So the correct answer is maybe I'll just write that options A, B, D are correct. But I'll just underline this. Maybe we should move the second question to the next page. So the second question is okay, this is like more of based on the definition of the extensive form games. So consider the following figure. So in this figure, like it's just a part of an extensive form game. So there may be like it's just part of some game, like, and we have to answer whether this is part of an extensive form game or is it not an extensive form game. So here, like this is the start node in the figure in this game where player one, so the first node belongs to the player one, and then these two nodes are belong to the player two, and then this third node belongs to player three. And then there are some like outgoing edges, and there is some further part in the game also. But considering just this part of the game, we have to answer can this figure represent an extensive form game? Okay, maybe I should write can the above figure. And why am I writing can? Because like this is not the whole game. Like there can be some out like we have not yet written the payoffs or anything, but there can be a whole game like under this also. But we are just looking at a snapshot of the game. And uh can this part be part of a extensive form game or not? So can the above figure represent? Okay, maybe I should write like this. The above figure cannot represent an extensive form game. Or and the above figure can represent. Yeah. The figure can represent extensive form game. So what do you think, Manas? Do you think that this can represent an extensive form game or can it not? Okay, so Manas says that we cannot represent this cannot represent an extensive form game. And why do you think so, Manas? Yeah, exactly. So good job, Manas, that because of child node convergence. So yeah, so basically what this means is so like so Manas is saying child node convergence, but just to simplify this, so what Manas means to say, so that we have actually obtained a cycle here. So you can say that like two parents are converging to the same child, and that's why it's not a extensive form game. But this is similar reasoning to saying that like there exists a cycle in the game, and we had already discussed that in an extensive form game, it is always a tree. Like this part was important in the definition of an extensive form game. So an extent and what is a tree? A tree is a graph which does not have any cycle. So, but here we indeed obtain a cycle. And note that like you may say that, oh, like if we consider the edges as directed, then there is no cycle. But note that uh, when talking about extensive form games and their cycle, like we are considering the undirected form of the game. Like if we consider edges as undirected, and if we and considering the edges as undirected, we obtain a cycle, then we'll say that the game is not an extensive form game. And here you can see that if you consider these four edges, these edges are actually forming a cycle if the edges are considered to be undirected. And so, yeah, this is not an extensive form game actually. So answer is okay. It's this option B. Maybe I should just find this as there exists a cycle in the above game, but an extensive form game cannot admit a cycle. And what's the cycle here? The cycle is between the nodes. Okay. Between the nodes 1, 2. Okay, maybe like I think the cycle is evident. Maybe I should not. Otherwise, I'll have to label the nodes also, which I don't want to do. Yeah. Okay, so I hope okay, so Manas is saying if we create a pseudo copy of 3 connected to unique parent, then yes, we can represent. So yeah, so exactly Manas. So if I have to, so that's a very good observation actually. That if I represent the extensive form game like this, okay, like this is not an extensive form game. This is definitely not an extensive form game. But suppose I had to represent this game, the game given to me in form of an extensive form game, like uh this is the game which I'm playing, but like it's not in its extensive form. If I have to convert it into its extensive form, what I can actually do is I can create two copies of this vertex 3, and one copy will just be connected to this left side 2, and one copy will be connected to right side 2, and then the game will indeed become an come in its extensive form, because then these two edges like having different parents, this vertex having two different parents, this problem goes away, and every vertex will now have a unique parent, and then we can represent the game in an extensive form. So yeah, so this is not an extensive form, but it can be converted into an extensive form. But uh, the above, like exactly this figure is not 10x, like, but the question as the above figure can represent an extensive form game. So no, this figure is not representing an extensive form game, but it can definitely be converted into extensive form if you like split, like if you create another copy of this 3 and just connect one copy to 2 and another copy to this 2. So that's a very good observation, Anas. Good job. So now maybe we can go on to the third question. Okay. So the third question is just again a true or false question. So the third question says that so again it's like which of the following are not true. So again a true false based question, and uh maybe we can go option by option here also. So option A is a tree with a loop can represent an extensive form game. So this is what we discussed just now, that if there is a loop, like loop means just a cycle. So this cannot represent an extensive form game because yeah. an extensive form game needs to be in form of a tree, and a tree does not admit a cycle. Like the statement actually does not even make sense. A tree with a loop. A tree is inherently something which does not have any loops. So what do you mean by a tree with a loop? Anyways, so this is incorrect. As an extensive form game does not have any cycles. Okay, so now coming to option B, a node can be a descendant of another node in the same information set. So this is something which I just discussed, like which we just discussed while the being the definition that this in the extensive form game definition, like this is an assumption which some people agree with, some people don't. Which this is an assumption which a lot of people don't agree with, but you will see this assumption in the standard definition of an extensive form game. This assumption that no node is a descendant of another node in the same information set, which was like the assumption of not being absent-minded. So this is what we will be assuming that is part of an extensive form game, that this assumption of non-absent-mindedness. So this is actually like no node is a descendant of another node in the same information set. So yeah. So a node can be a descendant of another node in the same information set. So this is actually false. Like usually in an extensive form game, we'll be assuming that the players are not absent-minded. So this is incorrect actually. As it's usually assumed that the players are not absent-minded in an extensive form game. So again, like one might say it's up to the convention, like whether you're assuming absent-mindedness or not. But in the standard definition, we'll be assuming that there is no absent-mindedness. Okay, so then maybe we can move on to option C. Option C says that every node except the root is connected to the root by one and only one path in an extensive form game. So what do you think, Manas? Is this statement correct or? So this is, I think, more of a graph theoretic question rather than a uh, information, like rather than a game theory question. But anyways, so yeah, so Manas is saying that this statement is correct because there are no loops. So yeah, exactly, Manas. Uh, so since there are no loops, uh, there will always be like so there always exists one path. We know that there always exists one path from root to any node. And but if there existed two paths from root to that node, this would imply that there exists a cycle in the graph. And a cycle in the graph means like the game is not an extensive form game. So yeah, correct. So this statement is actually correct, as if a node has two paths, two distinct paths to the root, then it would imply that there exists a cycle, which is a contradiction, as an extensive form game cannot contain any cycles. So, so good job, Manas. So we had to identify in this question like which other following statements are not true. So only options A and B are incorrect. Option C is actually correct. So the answer to this is options A, comma B are correct. Maybe I'll just underline this also. So note that maybe I should not write correct, but like not true, because it might cause a confusion of like what do you mean by correct or not correct? Yeah. So this is that answer, options A. Okay, then now we have like fourth and fifth question, which are a bit more like non-theoretical questions, more on the numerical side. So we have a common data for a game for questions 4 and 5, and so we have to consider the following game. So in the following game, like player one plays first, and it has two choices of playing A or B, and like then player two plays at both times, and like one time player two has choice of playing C or D, second time player two has choice of playing E or F. And now we are given that. The game ends here. Like we'll be assuming that the game is a single act game, and the game actually ends here. And like we have not written the payoffs here because like the payoffs will be different for like problems 4 and 5. So I have not written the payoffs here. But yeah. So assume that the payoff of P1, P2 at the end of C, D, E, F. So C, D, E, F are 1, 2, 0, 0, 4, 2, 3, 1 respectively. Also, we'll be assuming that, okay, maybe we'll be assuming that uh, usually it's a convention that all or every player wants to. So, so this is a very common convention in a non-zero sum game. Every player uh, wants to maximize his or her payoff. So, like you, this like you can think of it as like maximizing, like whether wants to a player wants to maximize or minimize. Like if a player wants to minimize, then we can just consider that the player wants to actually maximize the negative of that, or something like that. So now the question here is the payoff of player one, player one and player two at the end of C, D, E, F are given to us like this. And now we have to answer the following questions. So yeah, we will go option by option. And note that every player right now wants to maximize his or her payoff. So this is a non-zero sum game. We'll be assuming that the game is non-zero sum. And so this will be true. So the total number of strategies for player one in the game is 2. So like this statement is quite easy to see that so for player one there are only like player one is the starting player, so player one has only like two ways to start the game. Either player one plays A or player plays B or he plays B. So there are just two strategies. Yeah. So this statement is correct as the player has only two strategies, that is playing A or playing B. And note that we are assuming everything is like we are right now considering only deterministic strategies. So we are like obviously if you are assuming like if like we also talked about mixed Nash equilibria and everything previously, right? So one might say that okay, maybe there can be a probability distribution over these two strategies A and B. Like player one, the player plays A with probability P and B with probability 1 minus P. But and then like there can be infinite number of strategies. But like for now, we'll be sticking with the deterministic strategies since like in extensive form games, like we have not yet discussed like mixed strategies and everything. So yeah, and throughout this session, we'll be assuming that we are dealing with deterministic strategies and not with mixed strategies. So in deterministic strategies, the player can just play A or play B. So there are just two strategies. And now the option 2 says that the total number of strategies of P2 in the game is 4. So what do you think, Manas? Like for the player 2, what's the total number of strategies for the player 2? Okay. So yeah, so Manas is saying that this option is true, that the total number of strategies is 4. So yeah, nah, good job, Manas. Like actually like, but uh okay, maybe what should I okay. So one thing to keep in mind here is yeah. So this is correct. But just I wanted to you, I want everyone to keep in mind that how do you count the total number of strategies actually? So like it's not like player one, player two has strategies like C, D, E, F. Like player two can play like something like C or D or E or F, and so one might say, okay, that's why we have obtained like four strategies. But this is actually not the case. Like how what does a strategy mean? So for player two, strategy is actually a function. So for player two, strategy is not like just a single action, but it's more of a function which maps like uh, the action of player one to like what the action player two will be playing. So like, this was discussed in the lectures also, but I just want to like concretely mention this again because I think this is a very important thing to remember that uh, player two uh, has the strategies for player twos will actually be functions, and the domain of the function will be actions of player one, and the codomain will be the actions of player two. So yeah, as there are four possible functions for player two, maybe I'll just mapping to, yeah, four possible functions for P2, which are, maybe I should just mention, which are the following. So, hmm, so F1, so the function one will look something like this. Like function one will look something like this, that suppose player has played like what's a good way to represent this? Maybe I should just write this function as F1. And what F1 is actually saying is so there can be two possible inputs to F1 which are like what player one has played. So player one can play either A or B. So there are two possible inputs for F1. So F1 of A is equal to something, and then you can argue about like F1 of B being equal to something, right? And yeah. And like now, what are the choices if for F1 of A? So after F1 of A, the player two has two choices, C or D. So let's say the function F1 is actually giving like uh, is actually assigning C to like F1 of A, and F1 of in F1 of B, like it's assigning something like an E. And similarly, there can be another function. Maybe I'll just copy this and paste here, and like there can be another function F2 such that F2 of A again maps to C, but F2 of B maps to F. And similarly, we can have another function F3 where F3 of A actually maps to now. Okay, so like now we have map C, like now we can map something like a different, like a D, like F3 of A is actually equal to D, and F1 of B we can map to something like an E, right? And then we can have the last thing as this is F2, this is F3. Okay, this is F3, this is F4. So this is again F4. So F4 of A equal to D and F4 of B equal to F. So these are the only four possible functions which we can construct. So note that like suppose they were like actually so maybe like I'll not write this down, but just for revision manner. So suppose there were actually minus three strategies going out of P1. And out of all three nodes, only like two possible strategies were going out. So what do you think will be the total number of strategies in that case? I suppose like we have this like player one currently has two strategies A or B, but though there was also a third strategy for player one. And out of that node also the player two, there were two possible like actions going out for player two. Then what do you think will be the total number? Okay, so Manas is actually saying that if there was another node, like if there was another action for player one, and then player two again had like two actions corresponding to that, then actually the total number of strategies will be six for player two. Are you sure, Manas? Or do you want to like think about it for 1 or 2 minutes? Because like I think note that like the point I want to emphasize is strategies belong to the function space. So I'll just repeat the question. So what the question is, so right now I have this kind of a game. Suppose instead P1 had another possible action. Okay. So P1 had another possible action. So there was another node, let's say, here. And now corresponding to that node, player 2 had two possible actions. So suppose player 2 had two possible actions here, corresponding to another node, uh, which came from like another action of player 1. Yeah, so good job, Manas. So actually the answer will be 8. So now I think you get it. Like, why will this be 8? So this is because like we have to construct the number possible functions, and note that functions are just mappings from input to output, right? So now there are three possible inputs, and for all these inputs, like there are two possible outputs. So so the total number of functions will be like 2 times 2 times 2, which will be 2 raised to power 3, which is 8. So yes, exactly, Manas. So answer is 2 raised to power 3. So now just adding a twist to it again. So suppose in the third strategy, in the third action which player one played, like there were actually three outgoing actions for player two. Instead of just having two outgoing actions for player two, suppose in the third action of player one, like there were three outgoing actions of player two. Then what will be the number of strategies for player two? Right now, I said that for all the three for all the three vertices of player two, like there are just two outgoing actions. But suppose one vertex had three outgoing actions. Yeah, then it will be 12. So good job, Manas. So actually, yeah. So the answer is just something like so again, the input corresponding to the third action of player one will have three choices. And here we have two choices each. So the answer will be 3 times 2 times 2, which will be like 12. Yeah. So this is just like I wanted to make this specific that how do you count the number of strategies? Yeah. And so like since we know that there are only four possible strategies for P2, so this option is incorrect. So this option C is incorrect, that there are 16 possible strategies, and it's not difficult to see why. Like we just said that it has four possible strategies. So it can't have 16 possible strategies, right? 4 is not equal to 16. And then coming to option D, we have that the utilities associated with all the Nash equilibria of the game are unique. Okay, maybe I should just give this question because yeah. Anyways, we are okay. Like let's just say we are considering this option D because the point of this question was to just maybe making you able to calculate the Nash equilibria. So the question says that so the option D says that there are only three Nash equilibria in pure strategies. So for this question, we'll have to indeed draw to find the Nash. So note that for finding all the Nash equilibria, there is only one way, like which we have discussed, which is to convert the game from its extensive form to the normal form, and then see which of the following pair of strategies correspond to a Nash equilibrium. So here also we'll have to do the same, that for finding out the Nash equilibrium and pure strategies. So we'll have to uh, for all possible strategies of the two players, we'll have to form a payoff matrix and see which strategies correspond to Nash equilibrium. And note that the matrix which we'll be forming, the matrix will have something like two rows because player one only has two possible strategies, but it will have four columns because player two has four possible strategies. So yeah, the normal form for the game, the the normal form, which maybe can be just thought of as a payoff matrix for the game, will look like the following. So we'll draw the normal form of the game now. So we'll convert this extensive form game to its normal form now. So how do we do this? So we just make the payoff matrix for the game and like for payoff matrix. So the matrix, as I said, will have like four possible strategies for player two and two possible strategies for player one. And like just for including headers and everything, I'm just including one row and one column. So something like this. And now, like yeah. So in the normal form, we have player one, player two, and like so the column player is basically player two, as we have like usually that's the notation which we use, and like the row player is player one. So player one strategies are just playing A or B, and player two strategies are like these four functions, which are F1, F2, F3, and F4. So F1, F2, F3, and F4 are the four possible. Uh, Maybe I'll just put them in bold so that we know that these are more header-like thing. And yeah. Okay. So okay. Okay. So Manas is actually saying that since both are maximizing, in this case, we can avoid the normal method and directly say E is Nash equilibria only for this case. Okay. So Manas is saying that since both the players are maximizing, then like we can try to see like we can try to find the Nash equilibria uh, by just seeing the maximizing kind of a thing. Okay, I think uh, like it will depend on the values, but note that Manas in general. Okay, so Manas is saying that 4, 2 both received in maxima individually. Oh, okay, now I see what you're trying to say. Okay, the question's data is such that in this question maybe uh, the players will have only one equilibria, but still like maybe we should see it in form of a normal form also, just for like just because uh, I see your point that for the strategies like for the 4, 2, no one will have any incentive to switch because these are individually the maximum. But maybe I don't know, like maybe this 1, 2 also can be an Nash equilibria. I don't possibly know, but like it can be checked like whether it is or it is not. But why I'm saying this because like this two is also a maxima, so maybe player two won't have any incentive to switch, and maybe like player one's choices are such that it won't have any incentive to switch either. Maybe let's just see this in the normal form. So okay, the data is here and payoff matrix is here. How to have it everything on the same page? Okay, maybe we'll have to go a bit, or maybe I can just zoom out a bit if it is okay with everyone. Okay, so so this was yeah, I think it's a bit inconvenient to see it like this, but maybe let's just see it like this only. So I hope the screen is visible somewhat still. And so let's see if player two decides to play the strategy F1. So this is the strategy for player uh, one. Okay, maybe we Yeah, now it's okay. I hope now it's visible. Right. So for player one, if player one decides to play A and player two decides to play F1, then F1 of A, the outcome will actually be equal to C, because player one will actually be playing C. And the outcome corresponding to C gives the payoffs of 1, comma 2. So the payoff for the two players row, comma column player is 1, comma 2 here. So 1, comma 2 here. And now if player 2 decide to play F2, but player 1 decide to play A only, then again the outcome was C. And in this C again the payoff for 1, comma 2. And again, if we are talking about F3 and player 1 still playing A, then the outcome is actually D, and the D's payoffs are 0, comma 0. So this is 0, comma 0. So I'm just doing it step by step so that it's clear to us how to convert an extensive form game to a normal form. It's not really that difficult, but just for the sake of completeness. And again, if player 2 decides to play F4 and player 1 plays A, then it's the outcome, the player 2 will be taking the action F4 of A equal to D. And at end of D, the payoffs are something like 0, comma 0. Right? And now let's move on to if player one was actually playing B. So if player one was playing B and this was F1, so F1 of B is actually equal to E, and E's payoffs are 4, comma 2. E's payoff is 4, comma 2, and F3 of B is actually equal to, okay, like this is F2, not F3. So note that if player played B and this player played F2, then F2 of B is actually equal to F, and in this F, the payoff is 3, comma 1. 3, comma 1. And then F3 of B is again E, and in E, the payoff was indeed 4, comma 2. And here, and in the last, it will again be 3, comma 1. Okay, so this is the normal form of the game. And now we have to identify the possible Nash equilibria here, right? So how many Nash equilibria will be in this game? So let's just see here, maybe let's just see it entry wise. So let's just consider this entry 1, comma 2. So now actually we can see that since both the players are maximizing the payoffs, the row player will have an incentive to switch to the other strategy, because row player's payoff is currently 1 and switching to B will give a payoff of 4. So this point is definitely not a Nash equilibria. Similarly, if we see here, then again the row player has an incentive to switch since payoff goes from 1 to 3 on switching. So this is not a Nash equilibria. Similarly here in this case, again row player has an incentive to switch, and here also row player has an incentive to switch. So note that this row kind of strictly dominates this row for player one's payoff. So what this means is that there cannot be any Nash equilibria in this row. But let's just see here. So at least for player one has no incentive to switch here because Nash equilibria will reduce. But does player two have an incentive to switch here? So let's see. So payoff for player two currently is 2. And note that player 2 can't get anything more because in all the columns, the maximum payoff is 2 only. So this indeed is a Nash equilibria. So maybe I'll just uh, color this cell if I can. I don't know. Okay, this should be something like coloring the cell. Yeah, yeah, maybe just map it as something like this yellow corresponds to Nash equilibria. Similarly for 3, comma 1, let's see okay, so row player does not have an incentive to switch, but let's say the column player has. So note that a column player definitely has an incentive to switch because column player's payoff currently is 1, and it can go on to 2 if the column player switches to something else. Similarly, in this case, 4, comma 2, again, Row player does not have any incentive to switch. Column player also does not have any incentive to switch. Payoff is just true. So this is also Nash equilibria. And similarly, in this 3, 1 column player again has an incentive to switch from 1 to 2. So actually, hmm, so so good job, Manas. You actually were correct that the only possible Nash equilibria are 4, 2. But note that there is not just one Nash equilibria here. So there are actually like Nash equilibria does not correspond to the actual payoffs, right? It corresponds to a set of strategies which give you that payoff. So here you can see that actually there are two strategies, which are F1 as well as F3 for player 2, and um, like two set of like strategy profiles which give this. So one is when player 1 plays B and player 2 plays F1. Second is when player 1 plays B and player 2 plays F3. So actually in this there are two Nash equilibria. So it can be seen that the highlighted cells are the only Nash equilibria in the above game. Hence, there are only two Nash equilibria. So this statement claiming that there are three Nash equilibria in pure strategies is incorrect. So in pure strategies, yes. So I hope this makes sense. One is that like you said that correctly that 4, 2 is the only possible Nash equilibria. But what this means is that 4, 2 is the only possible payoff corresponding to Nash equilibria. But note that there can be more than one Nash equilibria which give you those payoffs. So yeah, here there are two payoffs. So option D is also incorrect. So only options A and B were correct, C and D were incorrect. So maybe I'll just write this down. It's only options A and B are correct. Now maybe we can move on to the next question. So fifth question is again for the same game, uh, but now yeah, the payoffs are different now. So we have the same extensive form game, but the payoffs for CTEF are different now. So what we have to do is just maybe we have to find out the Nash equilibria, find all the Nash equilibria and pure strategies in this kind of a game. And so what we can do is maybe so what we'll have to do is we again have to convert the game into its normal form. And we'll have to change the entry specifically, we have to change the payoffs corresponding to these payoffs now. So maybe I'll just copy uh, the previous game and just I'll keep the functions for player 2 since the extensive form was the same. So I can consider these four functions as the functions for player 2, and there are only two possible strategies for player 1, which are A and B. And now we have to see and maybe I'll just remove the color here. Yeah. And we'll have to rewrite these payoffs. Yeah. So let's see what was F1 of A actually equal to. F1 of A was actually corresponding to C. And what's the payoff for C here? Payoff corresponding to C is 2, 2. Similarly, F2 of A was also C, and so C's payoff is 2, 2 when the player 2 plays C. And now what was F3 of A equal to? F3 of A was D, and the payoff corresponding to D was something like 1, 0. So I'm just doing this a bit fast. I have to go a lot up and down here because this function is a bit, this question is a bit long, but I hope you get the argument which I'm trying to do. I hope everyone gets the argument which I'm trying to make here. So now, and now F4 of A is again equal to D, and D's payoff we know is equal to 1 comma 0. And now let's see like what is F1 of B. F1 of B is equal to E, and E's payoff is 0 comma 1. And now like F2 of B was actually equal to F, and F's payoff is like 1 comma 3. And you can actually see that F3 of B is also equal to E only, and E's payoff is 0 comma 1, and then last will be 1 comma 3. So this will be 0 comma 1, and this will again be 1 comma 3. So this is the normal form of the game for these updated payoffs. And now we have to like and the convention is every player wants to maximize their payoffs, and now we have to find the Nash equilibrium in this game. So let's see here. So let's see this point. So it can be seen that row player does not have any incentive to switch. And similarly, column player also does not have any incentive to switch because the payoff 2 is the like maximum payoff which the column player can get. So this is, yeah. Okay, where did we get the color from? Was it something like here? Yeah. Yes. So this will actually be an Nash equilibria. And similarly, again, this 2 comma 2 will also be an Nash equilibria because again, column player and row player will not have any incentive to switch. So again, this will be an Nash equilibria. Now let's see this 1 comma 0. In this 1 comma 0, it can be seen that the column player will have an incentive, row player will not have any incentive to switch because 1 is greater than 0. But column player will have an incentive to switch like from F3 to F2 or F1 because payoffs here are 2 and not 0. So this is not Nash equilibria. And similarly, this will also not be a Nash equilibria. And now let's see here. Uh, Here it can be seen that row player will have an incentive to switch because the row player has a payoff of 0 and will get a payoff of 2 on switching. Here also row player will have a incentive to switch. And in this point also it can be seen that row player will have an incentive to switch because 1 is greater than 0. But in the last case, row player will not have an incentive to switch because 1 is equal to 1. And it can be seen that column player will not also have an incentive to switch because column player's payoff is currently 3, and 3 is the maximum payoff that the column player can get in this row. So column player and row player both don't have an incentive to switch here. So this is also an Nash equilibrium. Okay. So yeah. So there are actually like these highlighted points are the Nash equilibria, and so note that there are only 3 Nash equilibria here. So one thing which I want to highlight here is, okay, so Manas has dropped out, but what Manas earlier told, previously mentioned was that 4, in this question he said that 4 comma 2 is the Nash equilibria. And here we saw that all the like strategies corresponding to the payoff 4 comma 2 were indeed Nash equilibria. But note that here in this question you can actually see that it's a very interesting insight that the payoff for, so if a Nash equilibria corresponds to payoff for 2 comma 2, then this 2 comma 2 is also a Nash equilibria. But note that 1 comma 3, the payoff of 1 comma 3, like there exists a Nash equilibria where payoffs of 1 comma 3 here. But this 1 comma 3 is not a Nash equilibria. So just is a very small thing which I want to just highlight here because like this is what something Manas kind of mentioned, and like I want to highlight that uh, characterizing Nash equilibria by the payoff you get is dangerous. Like there can exist same set of payoff for the players. Like there can be two different strategy profiles which give the same payoff for the players, but one strategy profile can be a Nash equilibria and the other may not be a Nash equilibria. So it is totally possible. Like it is like what's happening here also. Like this 1 comma 3 and this 1 comma 3. Oh, one might think that since one of these is an Nash equilibria and the payoffs are the same, the other also will be an Nash equilibria. But this is not actually true because this is an Nash equilibria, but this is not. And why is it the case? This is because of the inherent definition of Nash equilibria that Nash equilibria means that no one wants to switch. But here it can be seen that row player will want to switch. But here row player does not want to switch. So yeah, this is a very important thing to remember. I think like since this issue is brought up. since this issue was brought up in the discussion. So yeah. So yeah. So maybe the answer to this, I'll just update the answer to this. So it can be seen that uh, the highlighted cells are the only Nash equilibrium in the above game. There are only three Nash equilibria in pure strategy. So three is the answer. Yeah. Okay, so I hope this is clear to everyone. And this important point of this 1, 3 not being a Nash equilibria, but this 1, 3 being a Nash equilibria. So yeah. Okay. So since we have like done this fifth question, now let's move on to the sixth question then. So sixth question says that let A be an n-person single act game that is informationally inferior to single act game B. So what this statement is saying is uh, so let's say there are n people and the game is a single act game. What this means is that all the n players get to play exactly once only. And this is the game A. And this game is informationally inferior to another single act game B. So informationally inferior games, this was discussed in the lectures already that what does informationally inferior mean that okay, that every player strictly has lesser information in the game A than the game B, since the game A is informationally inferior. And what uh, one might think of this as like the information sets of the game B are just a refinement of information sets of the game A. So something like that. I don't want to get into definitions again since these have been discussed in the lectures. So yeah. And then the so, so the problem asks us like which of the following are the correct options. Statement one says that every Nash equilibrium of A is a Nash equilibrium of B. So this was kind of already discussed in the lectures that yeah, that any so A is an informationally inferior game to the uh to the game B, right? So this was discussed that any Nash equilibrium of an informationally inferior game will also be a Nash equilibria of the like informationally superior game. And the high level argument of why this was true was because suppose there is a Nash equilibrium in informationally inferior games, and the game here is A, and the informationally superior game is, let's say, game B. Suppose there was a Nash equilibrium in game A, but it was not a Nash equilibrium in game B. So what this means is there exists a strategy profile in game B, which is uh, better than the strategy profile of the Nash equilibrium of game A. But you could have simulated that new better strategy profile in the informationally inferior game itself by giving some constant strategies to some. So maybe I don't want to write this down, but like this was the high level argument and this was the proof was also given. So the high level argument is the strategies in an informationally superior game can be simulated as constant strategies in the informationally inferior game. So a Nash, so any so suppose there was a Nash equilibria uh, so yeah, so yeah, in the game B, a set of strategies which is better than like let's say the Nash equilibrium of the game A, then those set of strategies can be like uh, simulated as constant strategies in the game A. And so in game A, you will obtain something which is better than the existing Nash equilibrium. And that's why you can claim that any Nash equilibrium of game A will actually be a Nash equilibrium of game B. So statement one is true. But statement two that every Nash equilibrium of game B is a Nash equilibrium of A, this is like definitely false. Like B is a refinement, and like this, the kind of examples we saw also that like we saw that a game can be, let's say, there's an extensive form game, it can be decomposed into a simultaneous game and another dynamic game. Then there exists some Nash equilibria corresponding to the simultaneous game and some to the dynamic game. So simultaneous game is an informationally inferior game to the actual extensive form game, and like, but actual extensive form game can have two Nash equilibria, one corresponding to the simultaneous game and other corresponding to the like dynamic game. Whereas the simultaneous game only has one equilibria. So this is definitely incorrect. So so statement one is true, but and statement two is false. Actually, this is the correct answer. Option A is correct. And this is like kind of discussed in the lectures. Yeah. So yeah. But note that one important property is although every Nash equilibria of the informationally superior game is not a Nash equilibria of the actual inferior game, but any Nash equilibria of the superior game which can be like implemented in the inferior game also. So like what do you mean by an Nash equilibria of like superior game? B is like it corresponds to like set of strategies, and strategies are just functions here. So for the set of if the set of functions of the game B can be implemented in the game A also. And why am I saying can be implemented? Because like game A is informationally inferior, so it might be that the function takes some inputs, but in the game, some function corresponding to game B takes some inputs, but actually in the game A, like we don't have information about those inputs. So you can't implement those functions in the informationally inferior game. So that's why like any implementable, like any function which is implementable in the informationally inferior game, if it's a Nash equilibria in the superior game, then it will also be a Nash equilibria in the inferior game. So I hope this kind of high level idea makes sense. This was also discussed in the lectures, so I won't delve into that more now. Okay, but other than that, maybe we can move on to the next question then. Okay, so this common data is for question 7 and 8. So there are two games given to us. So the games are something like this also, this only that these are single act games where there are two players. So in the game one, player one has two choices, A or B, and then player two also has between those two choices like A and B, and there are different payoffs given to us for the games. And note that in the game two, again we have like the underlying game is the same, but note that these two nodes are being highlighted, and what this means is that these two nodes belong to the same information set. So actually, a player two cannot distinguish between these two nodes. So in game one, player two can distinguish between these two nodes. So player one knows what player one played, whether player one played A or played B. But in game two, player one cannot distinguish. So player one does not know whether player one had played A or played B. So this is somewhat a kind of a simultaneous game, because player one is already playing without any information, and player two also does not have any information of A or B. So this is kind of a simultaneous game. So game two, so just by changing the information sets but keeping the underlying game the same, uh, this happened that one was a dynamic game, other was simultaneous game. Okay, I'll just come back in 2 minutes, guys. I have to drink some water. I have to drink water, so yeah, I'll come back in 2 3 minutes. I'm just muting myself, right? So sorry for the break. So yeah. So like just changing the information sets made the game like earlier it was a dynamic game and now it's kind of a simultaneous game. So game two can be thought of as a simultaneous game. So pick the correct options. Seven question says that pick the correct option. It says that game one and game two are identical. Actually, like this is not correct. Yeah, maybe we'll go option by option. So option A says that the games are identical, so this is incorrect. As game two is an informationally inferior game because game two has lesser information, so it's an informationally inferior game to game one. So yeah. So option B says P2 does not observe P1's action in game two. So player two does not observe player one's action in game. So maybe I should just mention it here also, like uh, the highlighted states belong to the same information. So this might be confusing, like what does this correspond to? So maybe information set in game two. So these two states correspond to the same information set. Yeah. Yeah. Just mentioning this. So now like P2 does not observe P1's action in game two. So actually this is correct because uh, in P2, like in game two, these two nodes cannot be distinguished by P2, player two. And like these are the only two nodes which correspond to actions of player one. So actually, this is true that player two does not observe P1's action at all because player two has no way of knowing whether player one played A or played B. Correct? As uh, both the nodes of P2 are in the same information set. Now let's move to option C. So option C says game two is equivalent to a simultaneous move game between P1 and P2. So this is something which I already said also that since no player knows what the other player has played, so this is like some kind, this can be thought of as a simultaneous game only. So this is correct, and I don't want to get into discussion like, or maybe just write that. Uh, no player can observe others' actions in game two. Yeah. And now let's move on to option D. So option D says that P2 moves second after having observed P1 action in game two. So P2 moves second after having observed P1's action in game two. So this statement, as we have just said, that this is incorrect because P2 actually does not observe P1's action in game two because these two nodes belong to the same information set. So this is incorrect actually. So this is incorrect as discussed in option B. So yeah. So the correct options are only option B and C. So maybe I'll just underline this. Hence, options B, comma C are correct. Okay, now so eighth question is okay. Again, it's about picking the correct statements between the schemes. So, okay. So the statement A says that in game one, P1 has two strategies and P2 has four strategies. So note that in game one, P1 indeed has two strategies playing A or B. And what does P2 have? So P2 strategy profile will look something like possible functions. And what are the possible number of functions for player two? So again, like for if player one played A, then player two has like two possible choices for like f of A, and similarly player two has two possible choices for f of B. So total number of states will be 2 times 2. So this will be actually true. True. uh, so this is just true. Maybe I'll just write true. or maybe as P1 has strategies A or B, and P2 has four possible, has maybe I should write that 2 times 2, which is equal to 4 possible functions as strategies. Okay. But note that this kind of reasoning will not carry over to game two. So suppose the second option says that in game two, P1 has two strategies and P2 has two strategies. Like note that you cannot say that P2 will have four strategies in game two also. And why is this the case? Because earlier we were saying that the functions for P2 are like correspond to like the functions for P2 correspond to the inputs given by P1. Something like that was being argued. But now note that P1 cannot even P2 cannot even observe these inputs A or B. So P2 will now have the functions for P2, the strategies are like strategies we said was like for P2, the possible strategies are just some possible functions. But note that these functions will not have any inputs now because like P2 cannot distinguish between A or B. So there will be no inputs to these functions. So P2 can, so that's why we said that it's kind of a simultaneous game for P2. And so like P2 will have to play only A or B. So there are only two possible strategies for P2 now because P2 cannot observe P1's actions. So now there are no functions and there are just, yeah. So there are no functions and there are just these kinds of constant strategies for both player one and player two. So this is correct. So option B is true. Or maybe I should try correct. Yeah. So this is correct as P1 has strategies A or B, and since P2 can't observe P1's actions in game 2, hence P2 also has only two strategies A or B. So this can lead to like multiple interesting combinatorial questions. Like suppose there were multiple strategies for P1 and now there were some possible information sets and now you had to answer like what are the possible actions and things like that. These are kind of very interesting things and like you can just like you can make these interesting combinatorial questions. But let's not get into that. Like this question not all combinatorics. It's more about understanding like games and information's effects on games. So yeah. So yeah. So P2 only has two strategies. So now so in game one, options A and B are correct. So this directly rules out option C and D that P1 has two strategies, P2 has two strategies in game one or like something like this. So option C and D are incorrect. Option C, comma D, incorrect because of options A, comma B. So because A, comma B are correct, so that's why option C, comma D are incorrect. Now let's look at this option E. So what does option E say? It says that pure Nash equilibrium does not exist for the normal form of game two. So suppose this is the game two. So this is the game two which we have, right? And now we want to ask whether uh, a pure strategy Nash equilibrium exists in this game or not. So now for find out Nash equilibria, as I already said that we'll have to make up the normal. We have to consider the normal form of the game. So the normal form of game two is the following. So note that in game two, like there are only two possible strategies for player one as well as player two. So there will be like 2 x 2 possible strategy. So 4 possible strategy profiles. And now, yeah, maybe I just insert that table here. So I'm just drawing, I'll just now be drawing the normal form of the game. So there are, so 2 x 2 will the strategies and now just for headers and everything. This thing. So this is P1, comma P2. And now P in game two, Player 2 only has two strategies, A or B. Similarly, player 1 has only two strategies, A or B. So P2 will be the column player, P1 will be the row player as always. And yeah. So this is what we are doing. And these strategy profiles are in bold. And now let's look at the payoffs of the players. So if both players played A, then A comma A led to a 1 comma minus 1. So the payoffs are 1 comma minus 1. And note that every player is trying to maximize his or her payoffs. And like if player 1 played A but player 2 played B, what happened was player 1 playing A, player 2 playing B, the payoff was minus 1 comma 1. So I'm just again constructing a normal form. But now this is a different exercise because now I'm constructing a normal form for some kind of an informational inferior game. So it does not make much of a difference, but it's good to like just draw normal forms for some games to just practice it out. And now like let's say player 1 played B and player 2 played A. What's the payoff matrix now? So player 1 played B, player 2 played A. It's minus 1 comma 1 and last will be 1 comma minus 1. So it's minus 1 comma 1 and last was 1 comma minus 1. Right, this was 1 comma minus 1. So correct. Okay, so these are the four possible deterministic strategy profiles. And let's see in does there exist a pure Nash equilibria? Like if one of these strategy profiles corresponds to a Nash equilibria. So let's just consider this first. So right now you can see that player 1 has no incentive to switch because payoff is like 1 is greater than minus 1. But player 2 will have an incentive to switch because the payoff will increase from minus 1 to 1. Similarly, in this strategy, player 1 will have an incentive to switch from minus 1 to 1. In this, I'm just doing it a bit fast now because we are now comfortable, I hope, with Nash equilibria. Here it can be seen that in this kind of a thing, player 1 will have an incentive to switch from minus 1 to 1. And here it can be seen that player 2 will have an incentive to switch from minus 1 to 1. So in all of these cases, at least one player has an incentive to switch. So it can be observed that uh, none of the four possible strategy profiles is a Nash equilibrium for game 2. Hence, no pure. So we know that like mixed Nash equilibria will always exist. In this case, mixed Nash equilibria will be playing A and B with 0.5 probabilities because ones and minus ones need to cancel out. But let's not get into that. But in the pure Nash equilibria, it does not exist for game 2. Right? So this means that option E is correct. So what this means is option E is correct and options A and B were correct. So maybe just writing this down. Hence, options A, comma B, comma E are correct. Right. Okay, so I hope this makes sense for everyone. So if we are done with this, then let's move on to the last question for the day. It's the ninth question. So the ninth question says that pick the correct options and yeah, so there are four options. Option A is in a single act game, each player has only one information set. So maybe we'll just go option by option A. So again, these are like theory questions only. But yeah, let's just do this option by option. So in a single act game, each player has only one information set. So note that this is kind of incorrect. Like a player has only one information set in a simultaneous game. Like if a player has only one information set, then this means that player cannot distinguish between any pair of states, and this would correspond to something like a simultaneous game. But note that a simultaneous game is a strict subset of single act game. Like in a single act game, you can have a game with perfect information, right? Where uh, like every player like knows what the other players have played. So now like there will be multiple information sets. So this is incorrect. As there can be multiple information sets in a single act game. And just as a side note, that a single act game with only one information set is nothing but a simultaneous game, is just a simultaneous game, right? So yeah. So now let's go to option B. Option B is every edge in the extensive form game represents moves. So yeah, so in the extensive form game, like so moves is just means actions, and like every edge in the extensive form game means that some action has taken place by some player, right? So this is just like this is actually what uh, is the notation in the extensive form game. So this is correct, and like I don't think any explanation is needed for that, or maybe because like this is in the definition of extensive form game itself, or maybe just I was just calling the lectures. Like these are just kind of definitions for us. So yeah, we don't really have any arguments than this just being the definitions. And now option C is different extensive form games may have the same normal form. So yeah, actually this kind of a thing can also happen that like different extensive form games may have the same normal form. So this kind of statement is also correct because normal form is just a quick summary. Like normal form is just like as telling us about the different strategies and the payoffs corresponding to those strategies. But like those kind of final strategies can be arrived at through different extensive form games. Like these kinds of examples were also discussed in the lectures, so I won't be delving into this much. But yeah, so note that like just the key takeaways, different extensive forms can correspond to the same normal form. And this is not surprising because like, you can always have like different, you can all play around with information sets, the player sets and everything to obtain like two extensive games with same normal form. So in an extensive form tree, note that the player in question cannot distinguish are in the same information set. So again, like this is in the definition of information set only, that notes that the player in question cannot distinguish are in the same information set. So this indeed is correct. Uh, So this is also like discussing the lectures and like this is the definition of information set, right? If two nodes belong to the same information set, then the player cannot distinguish between the two nodes. So in this question, only options like we have to pick the correct options and only option B, C, D were correct. So yeah, the answer is I just write the answer. Hence, options B, C, D are correct. So okay then. So this was all I had for the day. So yeah, like these were the 9 questions. A lot of the questions today were mostly theory based only because like the lecture were also mostly theory only rather than like some numericals or something. But we also discussed like we also discussed some explicit examples of how to like convert extensive form games to their normal forms and uh like the finding out the number of Nash equilibria in an extensive form game. Like note that for finding all possible Nash equilibria, you'll always have to convert the extensive form game into the normal form because normal form is something which gives us like the precise information about Nash equilibria and everything. So yeah. So I guess this was it for today, guys. Since no one is present in the meeting in person, so like yeah, I don't think like I can't. So there are no doubts, like I presume, since there is no one in the meeting, like no one can ask doubts, right? So then I guess I'll be closing the session. So thanks for watching the session, guys. Hopefully, I'll see you guys in person next week. Same timings, Monday 6 to 8 p.m. So yeah, hopefully we'll see you guys next time. So goodbye for now.